It looks like something out of science fiction. A spacecraft with spindly arms, asymmetrical struts, and lattice-like structures that seem too delicate to survive the rigors of space. But this isn't fantasy. It's NASA's newest AI-designed spacecraft component, and it may be the future of space exploration. For the first time, evolutionary algorithms have taken the lead in shaping parts of NASA's most advanced missions. The results? Lighter, stronger, and radically more efficient components that no human engineer would have ever imagined. Before we dive into how AI is reshaping NASA's design process, make sure you subscribe, hit that notification bell, and give this video a thumbs up. We're uncovering the future of technology, one breakthrough at a time. NASA has begun leveraging what's known as evolutionary AI design, a process that mimics natural selection to iteratively refine and improve designs. It starts with a basic design brief, such as, make this structure as light as possible while withstanding launch stresses. From there, the AI generates thousands of design variations, tests them in simulation, and selectively breeds the most successful designs. Over hundreds of generations, the system hones in on bizarre but brilliantly efficient structures. These evolutionary processes allow AI to explore not only form and material distribution, but also entirely new approaches to solving problems rooted in physics and materials science. This technology isn't limited to basic shapes. It incorporates real-world physics simulations and detailed environmental data to produce results that are both novel and highly practical. Engineers are finding that AI designs can incorporate stress dispersal patterns, natural heat dissipation systems, and structural redundancies that emerge from evolutionary trials, not traditional planning. In a sense, the AI is tapping into a deep mathematical language of nature, speaking through vectors and stress fields to arrive at forms that seem alien, but work perfectly. Take for example the bracket that holds essential instrumentation in place aboard the upcoming Mars sample return mission. The final AI-generated design looks like coral fused with the frame of a spider web. It's 30% lighter than previous designs and performed better in vibration and stress tests. But if you handed that same design challenge to a human engineer, they'd likely produce a much bulkier, symmetrical structure. The AI, unconcerned with aesthetic norms, arrived at a solution optimized purely for performance. These designs challenge our very notion of what engineered systems should look like and often evoke awe, wonder, or confusion at first glance. This marks a dramatic shift in aerospace engineering. Traditional design methods rely heavily on symmetry, predictable geometries, and human intuition. Evolutionary AI tosses that rulebook out the window. The resulting designs often look alien or even chaotic, but they're mathematically precise and structurally sound. In fact, the components produced through AI design often outperform their human-crafted counterparts in strength-to-weight ratio, durability, and aerodynamic performance. NASA is no longer just building rockets, it is evolving them. It's a shift from static planning to dynamic emergence, letting the problem shape the solution through iterations guided by math and data. The implications extend to the entire life cycle of a mission. With lighter parts and greater efficiency, rockets can carry more scientific equipment, or even add redundancy systems without additional launch cost. That redundancy isn't just about safety, it's also about performance assurance under extreme conditions. Components designed through evolutionary AI are being tested to survive wide ranges of temperature, radiation, impact, and vibration, pushing the boundaries of current material science applications. That's especially critical in spaceflight, where every gram matters. Launch costs can run upwards of $10,000 per kilogram. By shaving off even a few hundred grams, NASA can save millions over the course of a mission. And in deep space exploration, less mass means more room for instruments, more fuel efficiency, and more mission flexibility. The implications stretch beyond cost. Lighter spacecraft can travel further, faster, and with more adaptable payloads. It's a paradigm shift in how we conceptualize mission planning and spacecraft construction. Reducing weight also translates into cascading systems improvements, smaller launch vehicles, less fuel, smaller support systems, and better thermal stability. But this isn't just about saving money. These AI-designed structures are enabling entirely new mission profiles. Because the AI can design around constraints that would paralyze a human engineer, NASA can now consider spacecraft configurations that were previously too complex or risky to pursue. This opens the door to modular spacecraft, adaptive structures, and even self-repairing components made from materials that evolve over time in response to their environment. The AI's creative problem-solving is forging a new kind of resilience. one grounded in flexibility rather than rigidity. Future spacecraft could literally change shape mid-mission to adjust to unforeseen environmental challenges or mission updates. If you're loving how AI is flipping spacecraft design on its head, subscribe, give this video a thumbs up and tap the notification bell so you won't miss the next breakthrough we uncover. Back to NASA. The agency's Jet Propulsion Laboratory, JPL, has become a hotbed for AI-driven innovation. JPL engineers collaborated with Autodesk to create a software platform called Generative Design, which uses cloud-based computation and machine learning to evolve structural designs. In one case, they used it to redesign a lander leg component, reducing weight by 35%, while increasing its load-bearing capacity. These gains aren't just incremental, they're transformational. Entire systems can now be reimagined around new principles of efficiency, inspired not by human guesswork but by cold, precise algorithms. This system has been dubbed a co-creator, not a tool, an AI partner in the art of space design. This partnership is helping shift NASA from a design-constrained institution to a possibility-driven innovator. Engineers are no longer limited by what they can manually prototype. Instead, they're empowered by algorithms that explore far beyond human capability. The computational power available to AI allows it to test millions of designs within a fraction of the time it would take a team of humans, vastly accelerating NASA's ability to iterate and evolve. And it's not just brackets and legs. Evolutionary AI is being applied to aerodynamic surfaces like antenna dishes, solar panel arrays, and heat shields. By optimizing the airflow and material distribution, these components reduce drag and increase energy efficiency, critical factors for any spacecraft navigating atmospheric entry or solar exposure. The benefits ripple out across every stage of a mission, from launch to landing, from power generation to thermal regulation. This multi-system optimization helps create spacecraft that are not only lighter but smarter, intelligently shaped to meet multiple performance goals simultaneously. What's more, these AI-designed parts are being fabricated with advanced 3D printing technologies, often using exotic materials like titanium alloys or carbon composites. This marriage of AI and additive manufacturing enables intricate geometries that would be impossible to machine using traditional methods. It's not just a new design paradigm, it's a new production ecosystem. These printed structures are often produced faster, with fewer steps, and with drastically reduced material waste. That's a sustainability win too, cutting-edge design with an environmentally conscious footprint. AI even plays a role in determining optimal material properties for different environmental stresses. And the AI isn't working alone. Human engineers still play a vital role in setting constraints, evaluating results, and testing physical prototypes. But instead of being the sole designers, they're now curators and collaborators, interpreting and guiding the machine's creative output. It's a fusion of human creativity and computational brute force. This collaborative workflow is reshaping what it means to be an engineer in the 21st century. Instead of mastering the CAD interface, engineers now master the constraints, goals, and training data that shape AI's creativity. One standout example is the lunar lander components currently being developed under NASA's Artemis program. Engineers challenged the AI to create a structural strut that could endure lunar temperature fluctuations, seismic activity, and landing shock. The resulting design resembled an organic spine, with branching arms and hollow cavities. Early physical prototypes not only met expectations but exceeded them. They were more resilient to stress, more adaptable to variance, and dramatically lighter than their predecessors. In subsequent tests, the AI-generated part even demonstrated micro-vibration absorption that had not been explicitly requested, a surprising emergent benefit. What might seem like a chaotic sculpture to us is in fact a masterclass in structural efficiency. The AI isn't just guessing, it's calculating millions of variables per iteration, exploring configuration spaces that no human team could ever manually evaluate, and each new generation of design gets closer to the elusive ideal of maximum performance with minimum mass. It's like evolution on fast forward, guided by physics and code rather than genes and generations. With each generation, the AI gains insight not from inspiration but from the rigor of testing, selection, and survival under constraint. Now, some skeptics worry about the interpretability of these AI designs. If no one fully understands how a component works, how do we ensure its reliability in space? That's a fair question, and it's led NASA to develop a rigorous testing framework for all AI-designed components, including stress testing, thermal modeling, and physical failure analysis. Redundancy is still built in, and engineers validate every critical element. NASA is well aware that trust in AI must be earned through performance, not assumed through novelty. Transparency in decision-making and outcome modeling is becoming part of the certification pipeline. Others question whether AI-designed parts can withstand the unpredictable challenges of space, from micrometeoroid impacts to cosmic radiation. Again, the answer lies in simulation. Evolutionary algorithms are trained on worst-case scenarios, incorporating extreme environmental data into their fitness functions. In many cases, the designs that survive these simulations are more robust than those produced by traditional means. These parts are engineered not only for strength but for survivability in the universe's most unforgiving conditions. They are stress-tested not in wind tunnels but in virtual nightmares. Even the International Space Station has begun to benefit. In 2024, a new mounting bracket designed by AI was delivered via SpaceX and installed externally by astronauts. It replaced an older, heavier component and offered superior vibration damping, which is essential for the station's sensitive equipment. And perhaps most importantly, it was produced faster and at a fraction of the original cost. Future iterations may involve live updates from orbit, structures reprinted on board to replace worn or damaged parts. So what's next? NASA is already envisioning fully AI-designed missions, spacecraft conceived, optimized, and tested almost entirely by algorithms. These missions could adapt on the fly, reconfiguring themselves based on real-time data, and even evolving in response to damage or mission changes. Entire mission architectures could become fluid, reacting to circumstances and optimizing themselves dynamically during flight. The spacecraft of the future might look different not just between missions but during missions, alive with change. It's not hard to imagine a future where AI designs the spacecraft, AI pilots it, and AI communicates with ground control. Human input would shift from direct control to high-level oversight, focusing on strategy rather than execution. This shift would allow NASA to scale its operations, managing more missions with greater complexity and less human bandwidth. The dream of self-directed robotic explorers, adapting and thriving in hostile environments, is coming into focus. Of course, this raises profound questions about trust, autonomy, and control. What does it mean to fly a mission you didn't design? How do we verify and certify an artifact we can't easily interpret? But for now, the results are speaking for themselves. Stronger, smarter, and stranger spacecraft components that push the boundaries of what's possible. And in doing so, they expand our understanding of what design can truly be. The frontier isn't just out there in space, it's inside our thinking about how things come into being. This is the future NASA is building, where AI doesn't just assist, but architects the next generation of space exploration. Subscribe, like, share this video, and turn on notifications so you never miss the next tech revolution. This is Tech Mythos.